Hi, welcome to Lesson 2.2, Inductive and Deductive Reasoning. Alright, so the very first thing we're going to look at in Exploration 1, which is on page 39, is what is a conjecture and how are we going to write a conjecture or draw a diagram using the conjecture that we are going to come up with. Alright, so first thing says write a conjecture about the pattern, then use your conjecture to draw the 10th object of the pattern. So as you can see here in the first triangle, you have a little dark spot on the bottom right, the second one bottom left, the third one at the top, and then as you can see, it starts repeating every 3 different triangles. So here you can see the sequence goes right, left, top, right, left, top. So it's going to repeat again every other 3. Now they want us to do the 10th one. Okay, so we would have the 7th, the 8th, the 9th, and the 10th. So all we know is that the 10th is where a new sequence starts. So just like number 1, just like number 4, just like number 7, number 10 is going to be exactly the same thing. Now you could draw 8 and 9 if you want to. You don't have to. But for number 10, the dot is going to go right there. Okay, so we observed a pattern and then we came up with a conjecture. Now for B, you notice that we have 2 things going on. You have curve and you have a line, and you also have the location of the quadrant alternating. So for example, this right here, that's a curve, that's a line, curve, line, curve, line, curve. Okay, so as you can see, all the even numbers are going to be lines and all the odd numbers are going to be a curve. So I know that the 10th one, it being even, is going to be a line. The question is, where is that line going to be? So let's just focus on the second one and the fourth one. Okay, so here, this line is in quadrant 4 and this line is in quadrant 2. Okay, the next even one is in quadrant 4. So as we can see, these are going to be alternating. Okay, so if I were to assume the 8th, the 9th, and the 10th, the 8th one is going to be on quadrant 2 and therefore the 10th one is going to be in quadrant 4. So it's going to be a line in quadrant 4 and it's going to look something like this. Okay, for C. Okay, you're going to be able to see that the full pattern repeats after, let's see, 1, 2, 3, 4, 5, 6 on the 7th one. Okay, but I want you to notice also one thing, that these right here, within these, they kind of flip if you see. You see how these 2 are the same as these 2? And you see how these 2 are the same as these 2, but you know they're flipped. So what would the 8th, the 9th, and the 10th be? Okay, so if you follow the same pattern, the 8th one will be like the second one, this one's going to be like this one, and this one is going to be like this one. So you're going to have triangle, triangle, circle, square. It's just a matter of playing around with the diagrams. Okay, exploration part 2. It says use the Venn diagram to determine whether the statement is true or false. Okay, so we're going to use that Venn diagram to determine it's true or false. If an item has property B, then it has property A. Well, B is within the limits of A, so yes, this is going to be true. If an item has property A, then it has property B. Well, this is false, because what if your whatever it is that you have is in here? Okay, so this has property A, but it does not have property B. So this here is going to be false. It's always good to know how to use a Venn diagram. All right, next page, page 40. Okay, if an item has property A, then it has property B. Well, you know that this is false because not all parts of property A have property C. So this will be false. For example, if it's right here, it has property A, but it does not necessarily have property C. It would have to lie in here. Now here's a question. Some items that have property A do not have property B. That's true. Anything within the limits out here, not including this, would be true. Okay, so for D, that is indeed true. If an item has property C, then it does not have property B. That's true because there is no overlap between property C and property B. So that itself is true. F. Some items have both property A and C. That's right. That's everything that's in the overlap here. So that is indeed true. G. Some items have both property B and C. That's false because there is no overlay between the property B and property C. So that's false. Now, just so you know where some of the problems are going to go, on that same page 40, okay, you're going to do problem number 6 right there and problem number 7 right there. So make sure you write down where they go. Okay, next page, page 41. Okay, problem 1 goes next to the word conjecture. Problem 2 goes next to the word counterexample. Okay, all right, and of course 3 and 4 go right there. Now let's talk about inductive reasoning. Okay, that's going to be a very, very important part of this chapter. A conjecture is an unproven statement that is based on only an observation. So pretty much you observe something and you come up with a conjecture. Okay. Now you can use inductive reasoning when you find a pattern in specific cases, and then you write a conjecture for a general case. So inductive reasoning is used to come up with that conjecture. Now you can either prove it, which we are going to be doing some proofs later on, or you can disprove it. Now, how do you disprove it? Well, we come up with what we call a counterexample. Okay, so to show that a conjecture is true, you must show that it's true for all cases. You can show that conjecture is false, however, by finding just one counterexample. A counterexample is a specific case for which one conjecture is false. Okay, so for example, if I'm standing in front of Edison and I see 100 cars drive by one after the other, and every one of those cars is red. So I'm going to make a conjecture that the next car is going to be red, or that all cars that drive in front of Edison are going to be red. We know that's not true because there's a lot more cars that will drive that are not red. So that would be kind of like my counter example. You know, it would be like one car that passes by that is not red. So we're going to look at counter examples in just a bit. All right, and example 5. Deductive reasoning. So there's a difference between inductive reasoning and deductive reasoning. Deductive reasoning uses facts, definitions, accepted properties, and the two laws that form a logical argument. So laws of logic, okay? So laws of logic to form a logical argument. This is different from inductive reasoning, where inductive reasoning is based on patterns. Okay? Now, here are the two laws of logic. The first one, excuse me, is the law of detachment. Okay, and the other one is the law of syllogism. So in the law of detachment, if the hypothesis of a true conditional statement is true, then the conclusion is also true. Okay? So for example, if I were to give you guys a true conditional statement, like for example, let me see, let me think of one. If you do not add gasoline to your car will die. I did not add gasoline to my car. So what's going to happen to my car? It's going to die. Okay, so that's the law of detachment. Now, the law of syllogism is kind of like a sequence of events. If hypothesis P, then conclusion Q. If hypothesis Q, then conclusion R. Therefore, if hypothesis P, then conclusion R. It's very wordy, but I'll give you an example. If you do not pay your cell phone bill, you are going to get a late fee. Okay, if you get a late fee, you're going to end up paying more in your cell phone bill. So I didn't pay my cell phone bill. Well, what's going to happen? I'm going to end up paying a little bit more. Okay, so it's like a little sequence of events that, you know. So if hypothesis P, then conclusion Q. If hypothesis Q, then conclusion R. Kind of like the transitive property. Okay, so if hypothesis P, then conclusion R. So let me put a little color in this. Okay, so it starts like this. If you have hypothesis P, then you have conclusion Q. Okay, if hypothesis Q, then conclusion R. So when you're writing this as one statement, you're going to have if hypothesis P, then conclusion R. Now, we do have several examples today. Okay, so bear with us. We do have 7 examples. All right, so let's get started with the very first one. Okay, here's example number 1. It says, describe how to sketch the 4th figure in the pattern. Let me see if I can get the line to be a little better. Okay, that seems to be a little better. Okay. All right, so you can see the first figure is divided up into halves. The second figure is divided up into quarters. The next figure is divided up into 6. So making a conjecture for figure 4, you can see that the denominator is going in a sequence of 2, 4, 6. So therefore the 4th one must be in 8ths. Okay, so in order to do that, you're going to draw a circle. We're going to cut it in half. We're going to cut it in 4ths, and then we're going to cut it again in 8ths. And then I'm going to shade one of those little pieces. Okay, so that's going to be in terms of 1/8. Okay, and that's example number 1. Okay, let's take a look at example number 2. Okay, example number 2. Okay, so read it. Okay, it says numbers such as 3, 4, and 5 are called consecutive integers. Make and test a conjecture about the sum of any 3 consecutive integers. All right, so here's what we're going to do. We're going to come up with a series of consecutive integers. The first one, of course, is going to be 3, 4, and 5. I'm going to come up with, 4, 5, and 6. And I'm going to come up probably with, 6, 7, and 8. Now, what I'm going to do is I'm going to add these. And then I'm going to come up with a conjecture about these. Okay, so 3 plus 4, that's 7 plus 5, that's 12. Okay. Haven't seen anything interesting yet. Okay, 4 plus 5, that's 9, plus 6, that's 15. Okay. So that's going to be 13 plus 8, that's 21. But let's take a look at something. all of these are divisible by the middle term. I don't know if you noticed that. Okay, because I can write this as 3 times 4. I can write this as 3 times 5. And I can write this as 3 times 7. So all these are divisible by 3. And I don't know if you noticed, but this term happens to be the second term. Okay? So my conjecture would be that the sum of any 3 consecutive integers is 3 times the second number. So my conjecture would be that the sum of any 3 consecutive integers is 3 times the second number. Now this is just a conjecture, okay? That's not necessarily mean that we haven't proved it yet. Okay, so if I wanted to prove it, there's ways that I can definitely prove this. All right. So the conjecture, conjecture is like an educated guess, is that the sum of any 3 consecutive integers is 3 times the second number. And you see the pattern? And of course, you can prove this. We're not going to today, but you can. All right, example 3. Okay, so a student makes the following conjecture about the sum of 2 numbers. Find a counterexample to disprove the student's conjecture. The sum of 2 numbers is always more than greater than number. Okay, well, let's see some instances where this might be true. Okay, so the sum of 2 numbers, say the 2 numbers are 2 and 3, that's going to be 5. Well, here, 5 is greater than 2, and 5 is greater than 3. Okay, so the sum of the 2 numbers is always more than the greater number, which is actually, I wasn't even supposed to do this one. Okay, so it's bigger than this one. So here, this is true. Okay, let's look at 2 other numbers. What about 7 and 5? Okay, that's 12. 12 is going to be greater than 7. Okay, that's not helping. I need a number that is not going to work. Now remember, it does not say what kind of number. It just says the sum of 2 numbers is more than the greater number. So what if I try some negatives? What if I do 2 plus negative 3? That sum is negative 5. Now, negative 5, is that bigger than the biggest number from here? The biggest number here is negative 2. And as you can see, this right here is not true. Okay, so this right here is false. So my counter example is negative 2 and negative 5, because the sum of those numbers does not satisfy that conjecture. Okay, and that's example number 3. Excuse me. Okay, example 4. If 2 segments have the same length, then they are congruent. You know that BC equals XY. Using the law of detachment, what statement can you make? Okay, so the law of detachment says that if you have a true hypothesis, then your conclusion is going to be true. So here you have that BC is equal to XY. BC is the length of a segment, and so is XY. So if I were to draw this, not that you had to, but if you had segment BC and you had segment XY, and they tell you that both of these have the same distance, that means that BC equals XY. Well, what's that going to imply? That's going to imply that these 2 segments are going to be congruent. So that will imply that BC is going to be congruent to XY. Okay, so let's read that again. If two segments have the same length, then they are congruent. You know that BC and XY have the same length, therefore the two segments are going to be congruent. And that's called using the law of detachment. Okay, we're going to take a look at the law of syllogism in example number 5. Okay, it says, if possible, use the law of syllogism to write a new conditional statement that follows from the pair of true statements. So both of these are true, guys. Okay? So let's take a look at this one. Now, in order to see if the law of syllogism works, you have to make sure that the conclusion of one of the statements is the hypothesis of the other. So even though these are not in order, you can see here that this conclusion is the same as the hypothesis for this one. So here, this will be like my P. If P, then Q. If Q, then R, lowercase r. Okay, so here you can apply the law of syllogism. Okay, so how would you write it? You would write it like this. If P, which is x greater than 5, then R, x squared greater than 20. Remember, the conclusion of one of your statements has to be the hypothesis of the other. Let's see if you have the same thing here. Here you have, if a polygon is regular, then all the angles in the interior of the polygon are congruent. If a polygon is regular, then all of its sides are congruent. Here you notice that they both have the same hypothesis. So here you cannot apply the law of syllogism. Okay, so law of syllogism does not apply. Okay? So just remember, the conclusion of one of your conditional statements needs to be the hypothesis of your second statement. Okay, so example 5 is there. Okay, let's take a look at example number 6. What conclusion can you make about the product of an even integer and any other integer? Okay, well, let's see. Come up with some examples. For example, how about 2 times 3? Okay, that's 6. Okay. What about 2 times 7? Okay, that's 14. They all happen to be even. So what about, let's see, what conclusion can you make about the product of an even integer and any other integer? Well, the thing is that no matter what kind of numbers you pick, like 4 and 5, you're going to get 20 here. So any number that is even multiplied by any other number is going to be an even number. Okay, so that is going to be my conjecture. Okay, that any even integer multiplied by any integer is going to give me an even integer. That one's easy. Okay, so that would be my conjecture. And of course, you can prove it, but we're not going to. Okay, now if I wanted to put this in terms of writing, you would write it like this. Okay. The product of an even integer and any integer is an even integer. And that's example number 6. Okay, if you need to pause it, pause it. If not, let's go on to number 7. Okay, it says decide whether inductive reasoning or deductive reasoning was used to reach the conclusion. Now remember the differences between inductive and deductive. Inductive reasoning, it's using patterns. Okay, deductive reasoning is using facts. Okay, so A, each time Monica kicks the ball up, it returns to the ground. So the next time Monica kicks the ball up in the air, it will return to the ground. So you see, here's your hint. Each time. Okay, so it's only based on a pattern. Okay, so in this case, this is an example of inductive reasoning. Okay, B, all reptiles are cold-blooded. That's a fact. Parrots are not cold-blooded, so Sue's pet parrot is not a reptile. To me, that sounds like it's a fact. So this is going to be deductive reasoning. And that's example number 7. Please make sure you complete your extra practice section and be ready for our live instruction in class. Have a great day.